So a binomial distribution, we have a fixed number of trials, whereas the Poisson distribution, we've got no real upper limit. Like, we can keep going for as long as we want. And, sorry, just like the binomial distribution, the Poisson distribution can only be described if we know enough about the event that's occurring to be able to write a function. So for the binomial, we needed the number of trials and the probability of a success from the trial. For the Poisson, to describe it, we just need the mean rate of the Poisson distribution to describe it. Okay, now this is the mean rate. What this is saying is, what is the expected value in that time frame? So the Poisson distribution is for a specific time frame. So for example, over one day, let's say an average of 10 cakes are produced in a factory. Okay, so they kind of come out at a constant rate. Baking a cake doesn't affect the when the next cake is going to be baked, so it kind of makes sense that this then fits. So we would say that for this, x is distributed by a Poisson with mean 10. So the mean for that time frame always goes in here. So this means that if I wanted to do the same for 2 days, what we should actually do is say that x is now distributed by a Poisson distribution with an average of 20. Okay. Now, it's important that you always scale to the time frame, because what can be missed if you don't scale up like this? Let's say if you thought, well, I can just do the Poisson distribution and then do it twice to look at it for 2 days. But this actually means that you've got a lot more different possibilities that you're thinking about. So let's say we wanted the probability that x is equal to 21 over 2 days. Well, if we did it the first way, option A, we could do the x equals 1 times x equals 20. So day 1, day 2, plus the probability that x equals 2 and x equals 19. And we could do this all the way over it. So we'd have 21 different probabilities. Whereas if we change our distribution for a different time frame, we just find that for this one, probability of x equaling 21. Okay, so whenever you're changing the time frame you're looking at for a binomial distribution, it's easier to just scale the mean up or down as you need to, instead of thinking about combinations of different, say, 10-day periods to make the overall 20 days or 2 days. Okay, so always scale to look at the time frame in the question. Now, if you need to find a probability, you have the equation in the data book that in general, probability that x equals x is equal to the mean raised to the power of x times by e, natural number, to the power of negative mean over x factorial. Okay. Now, this is not easy to put in a graph, but this can be put into table mode if you want. So you can type it into a table and it will give you different probabilities for each value of x. Okay. Now, if it's a non-calculator paper, this isn't the nastiest equation to use. Okay, so you could still be expected to use it in a non-calculator question. So if it isn't a non-calculator question, plug the numbers in. Also for non-calculator, let's say we've got the probability that x is less than or equal to 2, you will be expected to split this up into individual probabilities, because we can find those using the equation that we've got above. The non-calculator method is also going to be good if we don't know m, because we need m to be defined, I guess, or x. We need m and x to both be defined for us to be able to use this. As with binomial, the calculator method is on your distributions. And we use our PDF for when we've got the probability that x is equal to a number, and the CDF, as before, can only be used if we've got probability x is less than or equal to a number. So all the stuff we did with the binomial distribution, we can do as well with the Poisson distribution in terms of rearranging to get the region of the values that we want. Okay. Now, finally, something that is interesting about a Poisson distribution is the definition that the E of x is equal to m, and the variance of x is also equal to m. So if you're asked if Poisson is a good fit, or is a suitable probability function, there are a couple of things we can check. One, is it discrete data? Two, does it satisfy the conditions of sort of the roughly constant rate? So those are the ones that are above. And three, is the expected value of the mean roughly equal to the variance? And other than that, we just have now, let's do one or two past paper questions. So we'll do one which is a calculator question and one which is a non-calculator. But just before I move on to that, are there any questions about any of the stuff or ideas that we've looked at in today's topics? Perfecto. Okay. So like I said, I think I've got a nice non-calculator one for us to look at. A random variable x has a Poisson distribution. Given that x is greater than 0, has a probability of 3/4, find the value of m. Well, even when we got something where we don't know what m is, we never like probabilities that are cumulative, which are greater than, because we don't really have a way to do this. Like, x can go all the way up to infinity, so we need to limit it. So what we can say then is that all other events, which is just that the probability that x is equal to 0, what will be the probability in the comments of x equaling 0 given this question? So nice, exactly right. So that's 3/4. But we also have an equation in the data booklet, which tells us that it's equal to m to the power, 1/4, m to the power of 0 times e to the power of minus m over 0 factorial. Well, m to the 0 is 1, 0 factorial is 1. So we get that e to the minus m is equal to 1/4. If we take natural logs of both sides, we get that negative m is ln 1/4. So m is equal to ln or minus ln 1/4. If we take the minus inside as a power, that becomes ln 4. So there's our 3 marks, and we've satisfied the condition a is an integer. Now part B. Y has the Poisson distribution with 2m. So here we can say that m in this case is equal to 2 ln 4. Well, given the shape of this equation, we can see here that I've got, I've not got a number in front of this, and I'm going to be doing natural logs of it. So I'm going to call this ln of 4 squared, which is ln 16, which looks a bit nicer to me. Find the probability of y being greater than 1. Well, again, we don't want to do greater thans. So the probability of y being greater than 1 is equal to 1 minus the probability that y is less than or equal to 1, which is 1 minus the probability that it's 1, subtract then the probability that y equals 0. So this becomes 1 minus the mean, which is ln 16 to the power of 1, times e to the minus ln 16 over 1 factorial, which is 1, minus ln 16 to the power of 0, e to the minus ln 16 over 1. 1 subtract. Well, e to the minus ln 16, so that's ln 16 times 1 over 16. Again, we're going to bring the power onto the inside, so that's ln of 1 over 16, and we can get rid of it. Minus, well, this is now 1 times 1 over 16. So now we have 1 minus 1 over 16 minus ln 16 over 16. And it happens to nicely make, well, 16 over 16, subtract 1 over 16. So that's 15 minus ln 16 over 16. Now, something again we can be happy with, it told us we should have a negative. It told us that these C's should match and that this B should be different. So this satisfies the criteria for the answer. So there's a good chance that it's correct. I mean, I did it. There's a great chance it's correct. But seriously, if you are given it a form of the answer that it's meant to get into, if your natural working gets it to that form, I would see that and say, okay, probably don't need to worry about that because I've matched the form they wanted quite easily. I think that must be the correct method. Okay, they're going to give you sort of answer forms that are either intuitive or the way the answers come out normally. Okay, so that part B is kind of giving you a bit of help because it's a bit of a weird thing to look at. So they're saying, this is what you're aiming for. So we should have some logs, we should have some fractions. I hope you enjoyed the video. If you did, be sure to click down here to like, subscribe, and share with a friend. If you'd like to access the full online course, including the notes pages we were making, there's a link in our description below. Thank you for watching and good luck with your revision.